Hello, everyone. Welcome to my talk for the NCNGT 2021. My name is Mareike Pfeil, and I'm a PhD student at Heidelberg University. First of all, I want to thank the organizers for inviting me to give a talk and to talk about my research and things I'm interested in at this conference. My talk is about cataclysms for on-off representations. And in this video, I'll talk about cataclysms on Teichmüller space. It's meant as an introduction and to motivate why we are interested in cataclysms. First, I will talk about Teichmüller space. I will explain what earthquakes are. I'll talk about geodesic laminations, transverse cycles, and finally about cataclysms. So throughout this talk, let S be a closed, connected, oriented surface of genus bigger or equal than 2. In my pictures, it will always be a surface of genus 2. Teichmüller space, denoted by T of S, is the space of marked hyperbolic structures on S up to an equivalence relation. So what does it mean? Topologically, the surface is determined by its genus, so by its number of holes. But geometrically, it can look different. For example, I've drawn two different surfaces here. For the upper one, if we consider this curve, the separating closed curve, it's quite long. In contrast, the lower one, if we consider the same curve, it's rather short. So these two surfaces represent different points in Teichmüller space. Teichmüller space has a rich structure. For example, we can look at different sets of coordinates on Teichmüller space. And one example are Fenchel-Nielsen coordinates. They arise from dividing the surface into pairs of pans and measuring the length of the boundary curves of these pans, and also of measuring how those are glued together. And using Fenchel-Nielsen coordinates, one can show that Teichmüller space is homomorphic to R to the 6G minus 6, where G is the genus of our surface. Teichmüller space is a Kähler manifold, meaning it has a Riemannian structure as well as a complex structure and a symplectic structure. And these structures are all compatible. And this was shown by Violet Alphus. Another thing we can look at on Teichmüller space are length functions. So we can look at C as simple closed curve and on S. And if M is a point in Teichmüller space, so a hyperbolic structure on S, we can measure the length of this curve with respect to this metric. So Lm of C is the length of C with respect to the metric S, the M, the metric M. What can we do with these lengths? They can be used, for example, to compactify Teichmüller space, and this compactification is the Thurston compactification. I've said at the beginning there are several sets of coordinates, and apart from Fenchel-Nielsen coordinates, there's also the so-called shearing coordinates that have been introduced by Thurston and Bonahon. And these shearing coordinates are closely related to deformations of the surface, to earthquakes and cataclysms. So next, I will explain what earthquakes are. A basic example of an earthquake is obtained as follows. You take the surface S and choose a simple closed curve. I choose this separating one. Then you cut the surface along this curve and obtain two parts. Then what you do, you fix one part of the surface and twist the other against it. So twist here. And well, in my pictures, it still looks the same, right? You cannot really see that something happened. So I'll introduce an auxiliary curve. Look at the curve that goes around here. Oh, it's supposed to be closed. And if I cut, it looks like this. And now I fix the left part of the surface, but the right one I twist. So what happens here, it's still the same, but say I twist around once, and now the curve goes like this. And if I now reclue, this is what the curve looks like. This rather. So the topology of the surface didn't change, but the length of certain curves, for example, the length of the green curve changed. So we have a different hyperbolic structure now. And now you might have an idea, or at least this is what I imagine, why Thurston called this an earthquake. The different sides of the curves are moved against each other, just like the faults in a real earthquake. So this is just a very basic example of an earthquake. In general, earthquakes can be much more complicated. We can not only clue along one simple closed curve, we could choose several closed curves or a more complicated collection of geodesics on the surface. However, for earthquakes, we are only allowed to twist or shift in one direction. Why are earthquakes interesting? Thurston showed the so-called earthquake theorem that says for any 2 points, M1, M2 in Teichmüller space, there exists a unique earthquake map sending M1 to N2. So whenever I have 2 hyperbolic structures on my surface, I can find a collection of curves along which I can cut and twist and reclue such that this deformation deforms my hyperbolic structure M1 to M2. And this is why earthquakes are quite powerful and interesting. So what do we need to know for an earthquake? Well, we need to know where to cut. And this is given by a so-called geodesic lamination. And we need to know how much to twist, which is given by a transverse measure. And now I'll talk about geodesic laminations and transverse measures, or also about transverse cycles. I'll come to that in a bit, but first let's start with geodesic laminations. A geodesic lamination lambda on S is a collection of disjoint simple geodesics such that their union is closed. Well, look at an example. I've drawn our favorite surface of genus 2. We've seen one example before, namely one simple closed curve. This is simple, it's disjoint because it's only one curve and it's closed. So we could add other curves that do not intersect this one. For example, that one. Now, this is a pair of pans decomposition of the surface, and it's also a geodesic lamination. But we can not only add closed curves, closed geodesics, but we could also add bi-infinite leaves that spiral towards these closed curves that could look like this. So this leaf comes from there and then spirals closer and closer to this curve, and also on the other side it spirals to here. These are disjoint, simple, and the union is closed. Note that now we couldn't remove this curve, this closed curve, because otherwise the union would not be closed. So I could add more geodesic like this. For example, I could add one that goes from here to there and then spirals. I could add one that spirals like this, or I could also do that on the other side. Those all spiraling towards the closed curves. And now at this point, I cannot add any more leaves, no more geodesics. And such a lamination is called maximal. And for maximal lamination, its complement consists of ideal triangles, or parts that are isometric to ideal triangles. And I'll color one yellow for you now. So here, you might not see it right away, but this is an ideal triangle with one vertex spiraling around that curve from one side, one vertex getting closer and closer there. And yeah, same here. We could also draw this one yellow. By the way, these other parts are also triangles, isometric to ideal triangles. Just the way I've drawn it, you don't see it immediately. Now we could ask, okay, we have our surface S, it's hyperbolic, so we can lift it to the universal cover, S tilde, which is the hyperbolic plane, H2. And we can ask, well, what do these, what does this geodesic lamination look like in the universal cover? And this I have prepared. It looks roughly like this. So this is just a sketch. We have the red curves that are closed curves, and we have several lifts of them. And we have the green curves that spiral towards them. So they have the same endpoints at infinity. And I also colored some of the yellow parts, in the complement. And yeah, here you see you have the closed leaves, and you have these green leaves that are spiraling. There you have infinitely many copies that are getting closer and closer. And what you also see is that we have connected components of the complement of the lamination. So which are these yellow parts, or we also have the white ones that I didn't color. We can look at those, and those become important for the next definition, namely transverse cycles. So I fix a lamination lambda. And I've said before that for an earthquake, we need to know a transverse measure. But now, first, I explain to you what a transverse cycle is. So a transverse R-valued cycle, I call it epsilon, for the lamination lambda, assigns to every pair P and Q of connected components of the complement of lambda twiddle in the universal cover. And what does it assign to it? It assigns, it's a real valued cycle. So it just assigns a real number that we denote by epsilon PQ, such that, so we wanted to satisfy certain properties, epsilon should be, it should be pi1 of S invariant. Remember, it's defined for connected components of the complement of the lamination in the universal cover, but we want this to make sense also downstairs. So if we have different lifts of the same component of the complement, we want it to give the same number. So pi1 S invariant means epsilon of gamma P, gamma Q should be the same of epsilon PQ for every gamma in pi1 of S. I want it to be further symmetric. So that's just epsilon of PQ is the same as epsilon of QP. And lastly, I want it to be finitely additive in the sense that epsilon of PQ is the same as epsilon PR plus epsilon RQ whenever QR is the connected component that lies between P and Q, just as in this picture. And so this is a transverse R-valued cycle, and it's called a transverse measure if epsilon of PQ is non-negative for all P and Q. So these transverse measures are used as parameters for an earthquake deformation, and they tell you how much you have to shift for example, if you have had this basic example of an earthquake before, we have just one curve, one closed curve. And if you take the components of the complement that are next to this closed curve, epsilon of PQ tells you how much you have to twist. Okay, so what is a cataclysm or shearing deformation? Well, you start with a point in Teichmüller space, which is a hyperbolic structure on S, and you take as an input lambda, a lamination, and epsilon, a transverse. If I take a transverse measure, I get an earthquake. So I do the cut, twist, reclue thing, and I obtain another point in Teichmüller space. And this is an earthquake. But now I could also take a transverse cycle. And this is a cataclysm. So transverse measure gives an earthquake, meaning we can only shift in one direction. Transverse cycle is not a measure, so the values of epsilon can be positive and negative, meaning that we can shift to the left and to the right. So why do we care? I mentioned before the shearing coordinates. So it's a result by Thurston and Bonahon that if lambda is a maximal lamination, then for every point in Teichmüller space, there exists a transverse cycle, epsilon m, such that, for every point in Teichmüller space, there exists a transverse cycle, epsilon m, such that, okay, the assignment m maps to epsilon m is a homeomorphism from Teichmüller space to an open convex cone in the space of transverse cycles. This is what I want to show with this small cartoon here. So here I have Teichmüller space, and here I have the space of transverse cycles. It's a vector space, which I didn't mention, but you can convince yourself that you can add these and scale these. So it's a vector space. And if you start with a point here, M, you can assign to it epsilon m, which lies in this open convex cone. What does it have to do with cataclysms? If M1, M2 is obtained from M1 by a cataclysm deformation along lambda, then the transverse cycle giving this deformation is epsilon m2 minus epsilon m1. So these parameters, these coordinates are closely related to how we deform when we do a cataclysm, and they are called shearing coordinates. So why do we like these shearing coordinates? They are related with the structure of Teichmüller space. For example, I mentioned the length functions earlier, and length functions are convex in shearing coordinates, which is a result of Petzvina, Bromberg, Fujiwara, and Soto. And another example is that twist flows along simple closed curves. So the basic example that I showed you earlier, so if I just do this in Teichmüller space, those are Hamiltonian flows with respect to the Keeler form. So these deformations are related to the symplectic structure. So now I hope that I could give you a short impression of why cataclysms are interesting and that they reveal something about the structure of Teichmüller space. And if one is now interested in higher Teichmüller spaces or in an Ossoff representation, one can ask, well, might these cataclysms be a good tool as well in the setting of an Ossoff representations? And for that, one first needs to know, well, what are cataclysm deformations for an Ossoff representations? And this is a small advertisement for the second part of my talk, where I will talk about my theorem that tells you that cataclysm deformations exist for an Ossoff representations into a semi-simple non-compact connected Lie group G. So I hope you enjoyed this talk and that you also see my next one. And thanks for watching.